I just want to welcome everyone. Thank you for joining me on today's webinar Wednesday. Today's topic will be looking at the new SOLIDWORKS Topology optimization option that's inside SOLIDWORKS Simulation Professional and Premium. So we'll be going over kind of the overall workflow and what it is and what we can do with it. So today's agenda here is as follows. We're going to be discussing what is topology optimization. We're going to be discussing who topology optimization is intended for. We will also be talking about the difference between what we are probably used to in terms of the design optimization tools that were already available within Simulation Professional and above, and this new topology feature. We'll then be going over the interface, talking about what actually we need to define in terms of goals and constraints, and looking at how to incorporate load cases into it as well. And then, of course, more importantly, what do we get out of a topology optimization study? What are our results? What can we export? What can we use? And then I'll close it off by discussing some general tips. If you currently have used the tool or planning to use the tool, we'll go over that as well. And then any questions towards the end of the presentation. Okay, so first thing here, of course, we need to answer the question of what is topology optimization? Well, so I can kind of gauge where you guys are at in terms of what you've currently used through our design tools. I will like to throw out a couple more polls for you so I can kind of see what you're currently using and if you've used any other topology tool before we actually get into what it is. So the first one here is, I want to ask you if you are a current Simulation Professional or Simulation Premium user, if you have ever used a design optimization tool that's available with that. So if you can go ahead and kind of just let me know if you've already kind of familiar with the current process of our design optimization tool. That's the tool that allows us to define parameters, defining constraints through sensors, and defining a goal. So it looks like actually the majority of the audience here actually hasn't used that design tool. So definitely great that I'll be discussing what we currently have and what we can do now moving forward, or what we can also do with the topology optimization tool. But it looks like a good percentage of you have not used it, which is fine, but definitely will let you be aware of what it can do. Okay. So the other thing that I want to do is that I want to ask is, have you used any topology optimization? Maybe from SimulWorks, which is an option there, or if you're a current SOLIDWORKS Simulation Professional user, if you've seen it, or if you used it, or if you saw it in one of our What's New presentations, have you used it and how your experience has been with it? Well, it looks like we're having a little bit better numbers here in terms of if you've used the topology optimization tool specifically, which is great. If you haven't used the Simulation Professional one, hopefully you'll be in for a good show, because hopefully you'll find that it is really easy to use, yet very powerful in terms of what the results we can get out of. So definitely thank you for answering those polls. So now let's talk about, now that I have a better gauge in terms of if you guys have used it or not, is, well, what is this new topology optimization tool? Well, in Simulation 2018, under the What's New capabilities, SOLIDWORKS introduced this new functionality that is now available within Simulation Professional and Premium. And if you've ever heard of SimulWorks, that is another product that we sell, that we offer, which is more of a multi-physics type of analysis tool. And you may have heard of Tosca, which is topology is under that umbrella of different tools to optimize your design, right? So SOLIDWORKS Simulation is utilizing that technology to get a generic shape like what you see here, which is a picture of a bracket, and being able to specify different design elements or design criteria, goals that you want to optimize, like minimizing the mass, yet increasing the stiffness of the model, and still setting up the problem as you would in a normal linear static analysis, where you're saying things are restrained at certain points, loaded at a certain area of the model, and it'll iterate through kind of manipulating or kind of analyzing, where those fixtures are, the load directions in which you're applying, to get you a unique organic shape that you may not, have thought of, if you will, to optimize and meet the criteria that you defined. So it's a means to find an optimal shape of a component by applying optimization goals and geometric constraints. And we'll talk about what those optimization goals and geometric constraint options are as we kind of go throughout the demo of the tool. But an example of that, which I already mentioned, is the optimized shape can be based on minimizing the mass or wanting to minimize the mass through a certain percentage, while also increasing the stiffness, or maybe defining or saying that you want to minimize a certain max displacement throughout the entire model or in a specified location. So you'll see that you have quite a bit of different options here to set a criteria of what you want the tool to meet, and yet still giving you a unique shape that you may not have known to design or what direction to go in. So that being said, who is topology optimization for? Well, it's for anyone who, we throw around this word, we want to optimize. We want to optimize our design. We want to optimize our components. Well, it's for the designers who want to explore different design iterations, different design options to satisfy a certain design criteria, right? So as designers, you need to meet some sort of design criteria, whether it's, not increasing or not exceeding a certain stress level or not deforming a certain amount, right? In this case, we kind of can take some of those elements and take you into a direction where you may not have, considered a design option like what you see here that still satisfies those needs, right? So, the second point is it's for designers who are not sure the direction that the model should go in to satisfy those needs, right? Those design criteria. And if you've been running just a normal linear static analysis, a normal stress analysis where you're just checking your current design, to check whether it is exceeding a certain stress or it is going beyond yield, or checking to see whether it is below yield, right? It's now answering that question and then taking it further and saying, well, how can I make this better? How can I reduce the amount of mass yet still meeting a certain design criteria that I may have, right? So that's who the topology optimization is intended for. So essentially, any designer who wants to optimize some kind of current design that they may have, right? So that being said, you or some of you, based on the poll results, are aware and may have already utilized what we call a design optimization. And that is available within Simulation Professional as well. And we've had that tool for many years now. And I kind of am giving you a breakdown of one aspect versus the other. But at the end of the day, we now have two options to try to optimize and iterate through different designs based on, your kind of baseline part. So for a design study, it is a means to automate design changes based on material, geometric conditions like dimensions, or based off parent analysis conditions like changing the loads or the amount of loads or the load direction. And it's based off you defining constraints based off sensors that you say that it shouldn't exceed a certain stress, or it shouldn't exceed a certain displacement, or it can reference a parent study where, let's say you ran a frequency analysis where the constraint is your overall frequency mode should be between a certain range. So you are defining what those parameters are, and it can be any of those that I just mentioned. And they're based off these sensors where you're controlling what those criteria are. And then the optimization part of it is through a sensor as well, where you may want to minimize the mass of the entire model. And it's also good for, you can run this analysis for parts and assembly. So if you're not familiar, let me show you this quick animation of the interface. So right here, we're looking at an assembly of a press, and you see that I've woken up dimensions here. And what you'll see on the bottom here is I have two studies. I have a linear static analysis and I have a frequency analysis. So within a design study, optimization study, you need to run a parent study to so the optimization study can reference it to iterate through the different parameters that you want to change. And it's also a means to kind of say, well, I have this baseline assembly, my baseline parts, and I want to, see if that even meets my criteria, my design criteria that I may have, right? So you run those studies first, and then throughout the interface, you see that I have variables. In this case, I chose parameters of the dimensions of the actual physical parts. So I said that for the back height, I want to make sure, or my allowable range in which I can change this model or change that dimension is from one minimum value to one maximum value, right? So you're defining what those parameters are or what that range of allowable change you can make throughout the model itself, right? And then you define constraints where it's saying throughout the entire model or for specific areas of the geometry, you may want to make sure that it doesn't exceed a certain allowable stress or a certain allowable displacement, or the results of a frequency analysis should be between a certain frequency range, right? And then the actual optimization part goes into you defining this goal, which is one example of that is minimizing the mass, or saying that you want to minimize the factor of safety, or your result should be between a certain range of whatever it may be that you're running, right? So in this case, a design optimization study references your parent study. You choose the parameters that you want to vary, and then you define what constraints there are, and you define the goal that you want to optimize to. And then it runs through the different combinations, and you see that it physically changes the model in real time. And then the columns in red are the ones that didn't satisfy your design constraint, and then you get an optimized shape, right? You get an optimized shape there, and it's telling you that based on the criteria, this is the dimensions that model should be. So it's definitely a great tool. If you haven't used it, definitely worth checking out. But one of the problems with this is that it forces you to have a little bit of forethought on what those parameter changes can be. So you'll notice that in this case, I changed the parameters of the dimensions. Well, the key thing that you need to recognize is that all design changes are still parametrically linked. So that's how we model in SOLIDWORKS, where we have this parametric design where if I make a change to one thing, it may potentially make a change in another area of the model. So you have to have a little bit of forethought in terms of, well, if I'm saying that I want to change this dimension, how is it going to affect this other dimension that it may be linked to? And for those of you who have used the tool, that may be one of the limitations or one of the downfalls of it, or one of the frustrating things of utilizing that tool is, how do I know that I'm not going to break my model based on, that range of changes that I'm defining, right? So hopefully that kind of gives you a good idea of what that design study optimization tool does. But now, in contrast, we now have this topology study where it will produce a unique design model based on defining a best stiffness to mass ratio or defining manufacturing controls. So really the main difference is that the parameters that you change are a little bit more general or a little bit non-specific in terms of specific dimensions that you want to change. It's more of, I want to increase the stiffness and decrease the mass, right? And then from there, it will create a design option that you may not have thought of based on the initial design space. So you may hear this term utilizing this tool a little bit, initial design space. Essentially, that's your baseline model. So starting from your baseline model, you define the study the way you would in a normal stress analysis. And then from there, based on the optimization goals and constraints that you define, it's going to create a non-parametric changes to your geometry, where it's going to give you this unique organic shape that you would have not really thought of per se, in terms of still meeting the best stress or the best stiffness to mass ratio, right? So that'll make a little bit more sense once we go through the actual setup. But the optimized shape is could be based on the strength of the model, the mass, or any manufacturing controls, like, if it's going to be molded, how is the mold going to be separated from the actual part itself. And you can also reference multiple load conditions through defining load cases. So load cases is a feature, is a tool that's available within Sim Professional and above as well, to define multiple load conditions that a model will see, or that a model will endure, and you want to see what those results are. Well, it can take that information and help develop a unique shape through the topology study based on those different load conditions. And the other thing too, the last bullet there, is that we can only do a topology study on a single body. So we can't really account for it being in reference to an assembly. That's not really the point of topology in general. It's more of optimizing a unique shape, a unique body from your initial design space, and then trying to meet a certain stiffness goal, right? So those are the main differences between design optimization and topology. One's not replacing the other. There's just two options there that you'll see when you create a new study that you can do, right? So definitely let me know if you have any questions in regards to the difference. So let's go ahead and just look at the interface. So I'll go over the goals and constraints that you can define, the manufacturing controls that we can define, and what's going to interpret that information to give you, a unique shape. So what we're looking at here now is, in 2018, we have this model, or this assembly, I should say, of a hood hinge. So the hood hinge is going to be, this is raising the hood up and down. And you'll see that, all the other components are pretty detailed. We remove these areas of the model to reduce mass, right? But in this case, we created this bracket where it's pretty clunky. It's just one solid piece, if you will. We, of course, have the holes to attach everything, but it's not really optimized, right? It's not really reflecting the theme of what the other components have, right? So in this case, this is where the topology optimization study will come into play, because you may look at that model and say, well, I don't know what areas I can actually cut out from, or cut out to reduce mass, yet still meet the strength criteria that I need to do, right? So in a general workflow, you could jump straight to a brand new topology study without having to create an initial structural analysis. So unlike a design optimization study, it doesn't really reference the design, or it doesn't reference the parent study, the parent static study that you may have run. You can jump straight to it to try to get this optimized shape. But in my suggestion, or what I would suggest if you are planning to use the tool, is still run the analysis on the initial design space model. Because to me, it doesn't really make sense to optimize a part or optimize a body if it's already failing your design constraints, off that initial design. So if it's already not meeting your criteria, why am I going to optimize something if I'm pretty much going to be going in a bad direction, or going in a bad direction and maybe wasting time in the long run? So in this case, what I did was I created a static analysis on this initial workspace here, the initial design, and I just defined the typical things, right? Define the materials, define the fixtures, and where it's going to be loaded. And it's loaded in the direction in which it's attached to the hinge. The material that I'm using here is 6061 alloy, right? So we're utilizing this material here. And if we look at the yield strength of it, in terms of MPa, you see that my yield strength is about 55 MPa. So what I really just want to check for is that at the current setup, the current fixtures that I've defined, right, it's fixed at these holes, and then apply the force here. I want to run the analysis, and when I get my results, you see that I get an overall stress after it loads up here, hopefully under the yield strength of the material. And you see that it is looking about 40 MPa. So the yield strength, I believe, was 55. So it's well below the the yield strength. So, you know, we can evaluate this and see that there's high stresses in that area there, but overall, this should satisfy that design criteria, right? So this is what I would recommend as a starting point, but it's not necessary. At this point, you know, you can say to your boss or whatever and say, okay, well, that design will work, right? But now your boss wants you to minimize the mass, of course. You want to minimize how heavy this is going to be. You don't want to add extra weight if it's not needed. So in this case, what we can do is we can jump straight to a new topology optimization, or since the topology optimization study will require you to reset up the same setup in terms of where it's fixed, how it's fixed, what load condition, what load amount we're going to apply, we could just right-click and copy that study and copy those boundary conditions from the original static study to a new topology study here. So when I hit OK, you see that I just created a brand new study and it transferred over those conditions. So this is why, you know, it would be useful to run that initial study, because you're first checking to make sure that that baseline part works. And if it does, and you want to optimize it now, transfer those conditions to this new topology study. So you see that we have the single part. We just, you know, we're going to utilize the same conditions here in terms of fixture and the load, but now under this new study type, we get these two additional options here. And you see under goals and constraints, when I right click, these are the options that we have that we can specify in addition to the study what this design criteria is, right? So in this case, you see the first one, best stiffness to weight ratio, and then we see that it says default. Well, the recommendation here is that this is a good starting point to run a topology study in terms of, you know, making sure that, you know, things are going in the right direction in terms of, I just want to increase or get the best stiffness out of my geometry, yet minimizing the mass. The other options are just now a little bit more detail in terms of what you may need to define. But first, if I click on best stiffness to weight ratio, it's really simple to define. All you need to say is, you see that it recognizes what the current mass is, and then you say, well, how much do I want to reduce this by? Well, maybe I want to reduce this by 75%, right? And in this case, if I run the analysis, it's going to try its best to reduce it to this new final mass, yet still meeting the criteria of making it very stiff. It won't necessarily tell you whether it's going to go above yield or anything like that. It will give you an idea of what the stresses are, but ultimately what you'll get is some interpretation of what the shape could be, and then you can create that shape and rerun the analysis and see if it satisfies your design needs, right? So you see that I can reduce this to a certain percentage or reduce it to an actual absolute value, right? So it really depends on what criteria you need, whether it needs to be a specific weight. You see that I can also enable another constraint here, which is in reference to the overall displacement. So you see that for the overall model, I may not want it to displace or deform a certain amount, right? So you can have one goal, or you can have this combination of two goals, right? So you can say that I want it to, you know, not deform or only deform to a specific value or some sort of factor in terms of what we define here. And it's going to be either at the max point of that it'll figure out throughout the model, or you can say reference a specific point within the model by choosing some sort of vertex. All right, but the main thing here is what we recommend is starting off with figuring out the best stiffness to weight ratio. All right, so again, reducing the amount of mass, yet still trying to find the best stiffness. All right, so that's hopefully pretty simple in terms of recognizing or what that means. Essentially, you want to make it as strong as possible, yet minimizing the mass. And then very similar to what I already explained, you see that we have a goal where we can minimize the maximum displacement. So again, either choosing a specific reference. This is essentially the same menu that we saw earlier, which is saying that I don't want it to deform, referencing a certain point, a certain amount, right? So more of like if you have a deformation constraint. And then lastly here is the same thing in terms of minimizing the mass, but then in combination with the displacement. So you can have these goals be, unique, kind of specifying one goal, or having a combination of both, where you're still wanting to minimize the mass, yet still kind of defining a constraint that it shouldn't deform to a certain amount, right? So those goals and constraints are pretty straightforward and hopefully useful in terms of what you would consider optimizing a model. But we can go a little bit further in depth as well, where we can go into the manufacturing controls and we can say, well, I know in my baseline model here that there's certain areas of the geometry that I don't want to change or that I don't want to remove in terms of material. So for this case, it would make sense for me to say that I don't want to change, or I want to preserve, I should say, this face here and this face here and this face here, pretty much the cylindrical hole or the holes of the geometry, because these are going to be my fixture points. It wouldn't make sense for me to allow it to remove material there, because those are going to be the areas in which I am attaching the rest of the assembly to, right? So with the add preserved regions, really simple. You just specify the areas or the faces that you want to preserve, that you want to keep, that you want to save, and not have it change throughout the topology optimization study. So it's as simple as just selecting the actual faces here, right? And saying, I want to preserve those regions. Okay, the other things that we can do as well, and these are again more unique or a little bit more specific in terms of what your design criteria is. So maybe it shouldn't, maybe you need to have some sort of thickness, an actual specific thickness to the geometry. You can specify the thickness control, where you can say that the minimum thickness that you're allowing the model to be is whatever you define here. Or you can give it some sort of range by also defining the maximum thickness as well. So you're essentially saying that for my design, my thickness should be within this limit and this limit, or this minimum limit and this maximum limit, or just keep it simple and say the minimum thickness of the model should be at least whatever value you input there, right? So again, it's going to recognize this information and give you a result that will satisfy that criteria, right? The other ones that we have here is specifying the demold direction. So if this is something that, depending on how it's being manufactured, this will allow us to specify that this part essentially is going to be separated from a mold, or we're going to, essentially kind of have a mold here where we can specify what direction in which the mold is going to be extracted from the model, whether it's in one direction or in both directions. And all we need to specify here is some sort of reference point to say what direction things will be pulled. So if I say that it's going to be a mid-plane both directions, that means that the molding of this cast is going to be extracted or pulled from both directions of the model. So if I choose like this reference here, you see the double arrow is essentially saying that the mold is going to be extracted in both directions or pulled from both directions there. So it's really nice that we're able to account for even how it's manufactured. How is that going to play a role in the overall stiffness to mass ratio and things like that, right? So considering those manufacturing techniques. And then lastly here, we can also take advantage if your model is symmetric, quarter-symmetric, things like that, we can take advantage of that as well and help the analysis a little bit better by specifying the symmetry plane, saying that if my model was symmetric about a certain plane, I can specify that symmetry plane, and it'll help a little bit with the analysis, saying that essentially we're going to mirror those results onto the other side, right? So being able to leverage whether your part is symmetric or not, we can specify half symmetry, quarter symmetry, or even eighth symmetry, right? So and that's it. Really, we're hopefully what you're seeing so far is that we are utilizing a very powerful tool, technology from Simuli Abacus essentially, and we're throwing it into this user-friendly, very easy to set up, very familiar feel in terms of how, in terms of setting up this problem and still getting a good result, right? So, or a result that, will lead us in a good direction in terms of optimizing the analysis. So let me go into my completed set here, and I want to show you what the result options are. So as you run the analysis, you see that we still have to create a mesh, and there are some recommendations that I will have towards the end, but you'll notice that draft quality is enabled. And I'll go over a little bit here in terms of why that's okay, right? Because it's almost defeating, or it's almost contradicting what we would recommend in terms of we want to run it as a high quality mesh. Well, I'll explain a little bit later why draft quality is okay, but we still have to do our mesh, still have to mesh the model, and then when we run the analysis, we will get something like this, where, let me show you the image here, where we will be able to see what the overall shape could be, right? What the overall shape can be, and we can actually export this to a specific format in terms of a graphical representation, a surface body, or a solid body, right? So let's take a look at that real quick. You see that we can take a look, and what it'll create by default is this material mass plot, which is what we just saw in the PowerPoint here, which is being able to see the areas of the model that I can remove. And hopefully you can see this okay, but you see that the scale that we have is the ones in yellow are the faces that we must keep. So in addition to the areas of the preserved faces that I selected, it also mentioned that, or it's also saying that I need to preserve that top face, the bottom face here, and of course these areas here of the geometry. And then you see that the areas in which I'm okay to remove, which ultimately generated these pockets or these holes that I can kind of cut out through just a normal cut extrude of that original geometry. So pretty nice that we can get an idea of what that unique organic shape can be, essentially this optimized shape can be, based on meeting these goals, based on the original setup of how it's going to be constrained and loaded, and based on any potential manufacturing conditions as well, right? So you see that we get this representation of what we can keep, or what we must keep, and what we're okay to remove. And it also gives us the opportunity to kind of get an idea of what the stresses will look like through that optimized shape, right? What will be, what we'll be seeing, the higher stresses of the geometry is going to be very similar to what we saw in the original shape. We're seeing the stresses of this area of the model, right? So it kind of gives you a very first level view what those stresses look like. But ultimately now, what you would want to do is take a look at this material mass plot and get an idea of what changes you can make to your original model, right? So let's see here. So again, what we can get out of this is that interpretation of what we can keep, areas of the model that we can remove, and what can be kept. All right, so pretty nice what we can do here. The other thing that we can do, and actually I kind of forgot to mention this in the overall setup, but this geometry didn't have or isn't considering different load conditions as well. So in this case, the only load condition that we have is the force that we are defining on this face here, right? So if I hide this, you recall, I defined a force on that hole in a specific direction at a specific value, right? But what if this bracket had different load conditions? What if it was also being loaded kind of normal to the face, or any direction, if you will? Well, we do have this tool that we can run separately, outside of topology as well, which is when you run a normal linear static analysis and you want to run through different load conditions, we can run through this multiple load cases. The way to get that is we can right-click on the study and go to multiple load cases. And you see that it gives us this interface here. And the interface is recognizing what fixtures you have, what load conditions you have, and you can create multiple combinations or multiple criteria in terms of, in this scenario, I want to apply it at 200 newtons, the initial one, and this one I want to suppress it, or maybe I want to change the value to 150. So you can play around with different load conditions, and ultimately what it does is that it's going to take that information in addition to the original setup and in addition to the manufacturing constraints, and it's going to allow us to include those conditions, and by default what it'll do is it'll create an optimized model or an optimized shape that will maintain a proportional stiffness in each direction of the load. So what that means is that in every load direction, there's going to be some deformation, and essentially it's going to create an even distribution of stiffness in those directions of load, right? So really what this is saying is that not only can we just run a topology optimization study on a single load, but we can also do it in a combination of loads as well. Or the other option that we can do is if we go into our study options, we can enable this use min-max formulation option. And what this does is allows the study to reference the response of the loads and then stiffen the model in the direction or in the area of the model where it's seeing the highest deformation. So we can say that out of those different load conditions, one condition gave us the largest deformation or is deforming the most. Well, let's make in this formulation with this option on, it will increase the stiffness within that direction itself. So you can either have it be proportionally distributed throughout the entire model in the direction of the loads, in any direction of the loads, or you can say stiffen up the model in the highest deformation that it sees within the analysis. All right, so we didn't have that in this study here. We really just had the single load, the original setup, and those design criteria. But it's really nice that we can leverage this load case technology into the topology analysis as well, and therefore get a more accurate representation of what that optimized shape can be, right? So going back to what the study results are, well, what do you do with them? Or what can you do with the overall result? What's the intention of it? Now that I know that the areas that I can remove material, well, what can I do now? Well, the intention is now is that you see under the advanced options, I can export this to a graphical representation or save it as a external file, or you see that I can export the deformed physical shape as a configuration. And you see that under that, we get, excuse me, a mesh of the geometry, but you see that it's actually a physical part. So you see that it is a little choppy. It is something that you can try to work off and add features to. But in this case, the real recommendation currently as far as how we would interpret this or utilize this is we can export the graphics or we can export the physical geometry. And if we're exporting the graphics, we can essentially trace over the areas in which we can remove material, essentially just using that as a reference in a means to change the original model that you had and then making those changes, right? So exporting it as a graphic should be good enough because you're just using that as a reference where you can potentially trace over and create a new part. But if you really needed to, you can export it as a solid body or a surface geometry, but you are left with, again, a non-parametrically linked part. It's really just going to be a dummy solid and really just use as a reference for you to create your new geometry that could look like this. All right, so if I activate this configuration within the same model, essentially what we did was, recreate or actually add those features to the original workspace and say, well, the topology optimization told me to cut out these pockets here, potentially some areas in this area as well, and this could be my overall shape. So you're using it as a reference for you to redesign the original model to get something like this. And then, of course, after the optimized shape, you want to make sure that it still meets your stress criteria. You want to make sure that it's still well beyond or well below yield. So we can then set up the original problem, right? Especially if you kind of just added a configuration, we can copy the study from one configuration and apply it to this new configuration. And you see that the stresses are still in the area where we saw originally, but it's still under the yield strength of this material that we defined, right? So not only are we now meeting our stress criteria, we also minimize the mass of this new optimized shape. All right, so hopefully you have a better understanding of as far as how you would utilize this, how this can be beneficial, and what the overall workflow can be. And hopefully you'll see that it doesn't add much to the original setup in terms of the setup of the entire topology study. All right, so that being said, hopefully you kind of get an idea of what the overall workflow is. And now I want to just end this presentation with some general tips that you should take into consideration when running a topology study. Well, although it's not required, I still recommend running a structural study before running the topology study. Main reason is, again, it doesn't make sense for me to optimize a shape if the original shape is already failing your potential design criteria. So generate your generic model, run the stress test, make sure that passes or that satisfies your design needs, and then you can say, well, how can I make this better? How can I minimize the mass yet still, stiffen up the geometry? That's where topology optimization will come into play. The other thing is follow the best practices of the original structural study. So if you've taken our classes or you already have a good feel of running just a normal stress test, follow that same best practices because it's going to be needed in the topology study. We still need to define fixtures. We still need to define the loads and the material definitions. So making sure that your materials are okay or in the right units, things like that, right? So still follow that best practice in terms of how is my model going to be constrained? How is my model going to be loaded to best replicate what's happening in real life, right? The other thing is you'll notice that when you create a new study, it may default to a standard mesh. It may also default to a draft quality mesh. Well, in this case, a standard mesh with draft quality is recommended and is okay for a topology study. Reason being is because what's required as far as a good quality mesh is we still want to make sure that we have enough elements across the thickness, that we want to make sure that there's a lot of elements throughout the geometry, but a standard mesh is recommended because we need a good quality mesh throughout the entire model and the internal geometry itself versus just areas of concern. Where, in a regular stress test, we may add a mesh control or say that I want to refine the mesh in a certain area, which may be my concern. But in this case, we just need a good quality mesh throughout the entire geometry inside and out. So a standard mesh can do that for us. And a draft quality is also recommended because stress is not necessarily concerned when it comes to topology. The only thing that's really concerned is just removing mass and increasing stiffness, right? That's why I recommend doing the original stress test to make if stress, of course, is a concern. So save on computation time by just using a draft quality mesh. Those results would still be okay. The other thing that we recommend as well is using a direct sparse solver. If we utilize the iterative SFE plus solver, it's not good at handling large differences between the neighboring elements. And really what that means is what's really happening in the background when we're running a topology study is that it's eliminating the elements that are less stiff or almost soft, if you will, versus keeping the stronger elements or the elements that are going to be more stiff. So as it's iterating through, it's eliminating those soft elements, if you will, and keeping those stronger elements. So in an FFE plus solver, it just doesn't do a really good job in recognizing the differences between that element type and the other element type, right? So, and then lastly, in terms of the setup of the topology study, start off with the best stiffness to weight ratio default option. That's a good starting point. And then, of course, apply the other conditions as you see fit, right? And then if you do want to include different load conditions within the model, I do recommend getting familiar with the load case functionality. Load cases is its own unique tool that you can add to a normal static analysis, but it can also be used now in the topology study as well. Okay, so hopefully that was okay. Hopefully you have a better understanding of what the topology optimization study can do. Definitely let me know if you have any questions here, but that kind of does conclude what I had prepared for you in terms of showcasing that new feature. Okay. The other thing that I want to address here that doesn't relate to topology in general, but just be aware that, again, you're probably not new to this. We do these webinars every Wednesday. These are the upcoming webinars for the month of February here. The next one next week here that we will talk about is for electrical schematics, design better systems faster. So if you have electrical schematic or you just want to learn what electrical schematic is, definitely join in to that webinar there. The week after is talking about utilizing weldment features to do 3D printing. And then lastly, you may have heard that, you know, SOLIDWORKS CAM or CAMWorks kind of integrated a certain level of the tool into SOLIDWORKS in general. So it's going to discuss what the difference is between the full-blown tool and the one that comes with the tool with SOLIDWORKS as well. So definitely join us for that. You'll probably receive an email for that, or you can go to our website, hawkridgesys.com, and go to our events webinar section, and you can register that way. But again, I just want to thank you. If you have any questions, or if you want more information in terms of topology, definitely let me know, or you can contact your local account representative, and they can get in touch with the AE or even me myself. But definitely let me know if you have any questions there. I just want to thank you for joining me today, and I'll be sticking around here to answer any questions that you may have. Thank you for your time, and have a good rest of your day.